Let's have a look at this projectile motion question together. The question itself is quite straightforward, but I like to use it as an opportunity to discuss how we choose and set up vector directions. Once you understand the setup process, many vector problems become much easier to tackle. So before we begin, we need to recognize a hidden assumption in this question. Both the problem statement and the solution assume that the projectile moves through air and the air resistance is negligible. In other words, the only force acting on the projectile during its flight is gravity. This assumption simplifies the analysis and allows us to apply the standard equations of projectile motion. So with that in mind, let's look at how to establish a coordinate system and assign directions to the vector involved. One common approach when setting up a coordinate system is to choose the direction of the initial velocity as the positive direction. So in this question, the motion starts at point A, where the initial velocity is 150 meters at an angle of 20 degrees downward to the left. So let's have a look at the initial velocity here. So this is point A, and the way initial velocity goes is to the left with an angle of 20 degrees from horizontal. So if we resolve this velocity into components, we're going to get the x component is going to the left, and we can call it VAX. And the y component is going down, we can call it VAY. Okay, this is the original VA, and VAX and VAY are the components of VA. So therefore, I will define the coordinate system that the left is the positive x direction, and the down is the positive y direction. So this is my x, this is the y. So now let's calculate the VAX and the VAY together. VAX should be equals to VA times cos 20 degree, and VA is 150 meter per second times cos 20 degree. We're going to get 140.95. Unit is meter per second, and the direction is going to the left. Okay, and then VAY is VA sine 20 degree. So 150 times sine 20, we get 51.3 meter per second and going down. Okay, so once we get that, let's have a look at the part A of the question here. Part A, they're asking for the horizontal distance D here, over here. Okay, to solve that, we know that the initial velocity VAX have a number solved, and what we need is the time, the travel of the time. So how can we get to the travel time? We can get it from the y direction, which have a displacement, and that displacement is 20 meters. So we're going to start from the y, the SY, okay, displacement. The standard equation for this is we're using the initial velocity, which is VAY at y direction, times the time, plus half, and A is acceleration at y direction, times time square, right? So as we said, the only force applied in the system is gravity. So therefore, the gravity is contribute to the y direction acceleration. So now we decide that y direction going down as a positive, therefore the VAY, we're using the positive number, so 51.3 times time is what we're looking for, half. Acceleration at y direction is the number of the gravity, which is 9.81 meter per second square, and it's going down as a direction, and it's at the positive direction, right? And then time square. And sy itself is 200 meters. So here, going down, again, it's a positive displacement because I define going down as positive. Okay, so that's the equation we get. And this is a quadratic equation. If you want to simplify that, we get something like this. So 4.905 t squared plus 51.3 times time, and then we move the 200 to this side, so negative 200, and that's all equals to 0. This is a quadratic equation. We solve for t. We should get two t numbers. So the t1 I got is 3.03 seconds, and the t2 I got is a negative number, negative 13.49 seconds, which is not a valid number. So we're going to discard this one. You cannot have a negative time. And we're using the time, which is 3.03 seconds. Now, with that in mind, the projectile motion at the x direction is going to have the same time, which we're using t1. And then at x direction, because there's no force applied at x direction, the only force is gravity is acting down. So x direction, we should see a constant velocity. So therefore, let's continue with this question number, part A of that. We're looking for the distance d. The distance d, we need to use, this is actually the displacement at x direction. And we can use the VAX, which is the constant velocity, times the time we get. And if you want, the standard equation should be half ax t squared. But because this part over here, the ax is equals to 0, so the whole thing here is equals to 0. So we only have VAX times time here. VAX, we have a number, 140.95 meter per second, times t1, we got 3.03 seconds. And the total displacement here should be 427.1 meters. Or if you consider that as a displacement, it's actually going to the left, right? Displacement is a vector as well, so it has to have a direction as well. Okay, so that's part A of the question. Part B here, they're looking for the velocity just before striking point B, which is on the ground. So let's have a look at this here again. So at point B, what do we have? At B, before it landed. So we should see a x direction velocity. I'm going to call this VBX. and we should see a y direction velocity. I'm going to call this VBY. So once we get this 2, we are looking for the resultant of this 2 velocity, which is the VB here. That's the final one we're looking for. And also VB is a vector, so we're going to need an angle as well. We'll need this angle or the other one, up to you. Okay, so let's find out the VBX and VBY first. So VBX, well, this one is easy. At x direction, we have a constant velocity. So VAX is not changing, so it should be the same as VBX, and this number is calculated already, 140.95 meter per second going to the left. Now we need to find out the VBY. How to get VBY? Well, this y direction, we have a velocity change. So we start with the initial velocity is VAY, and then we need to add AT, which is the acceleration and the time, and acceleration has to be at a y direction, right? Yeah. So VAY, we know the number 51.3. Velocity is going down, gravity, so this is 9.81 again. I'm using the positive number because I define going down as positive. And then the time, I know 3.03, right? Before it landed. So VBY equals to 81.02 meter per second. Put down the direction is going down. Okay, so now I need the resultant of these two components, and it has a 90-degree angle, right? So VB should be equals to x component VBX square plus VBY square, and I get the square root of this summation. So that equals to 140.95 square plus 81.02 square. So we get the VB as 81.0. Did I copy something wrong? Yeah, I did. Sorry. So this number, VB, we get is 162.58 meter per second. Okay, and we know the direction is actually going down with a angle theta. And then we need to find out the theta before we draw the conclusion. So tan inverse, right? Okay, we have the VBY, which just the magnitude, and the VBX, just the magnitude. So that is tan inverse of VBY is 81.02, and VBX is 140.95, and you get 29.7 degrees as the angle. So as a conclusion, VB should be equals to 162.58 meter per second with an angle of 29.7 degree. Okay, so let me know if you have any questions. Thank you very much for watching. Bye now.